Trans-Carpathian seminar. We're back with our Trans-Carpathian seminar, safely past the All Fools' Day. And so it's a double pleasure, therefore, to introduce our today's speaker, Bartosz Prech, a local student who's going to introduce us to the subjects of contact integration through the symplectic lens, so to speak. So please.
Yeah. So, morning, hello everyone. I'd like to maybe start with a few words of gratitude for Mrs. Kasia for helping me and guiding me through the project, and for enormous numbers of email we probably sent one another during this cooperation. And as Rafa has mentioned, today my
Mr. Rafa. There's Miss Kasia.
Yeah. It is magnificent. Rafa has mentioned.
Please call her Prince Kasia. Except for her Kasia, not Miss Kasia.
Yeah. So.
Did you failed the first test? Now you may continue.
Yeah. So the topic of my talk is like contact integration wouldn't be actually a good word, because this will be a symplectic integration, but applied to contact system. So we will transfer the contact structure to a homogeneous symplectic structure, and then apply the known methods of integration. So here, as I mentioned, I will cite a few times during my talk these three papers that I used preparing my presentation. Here they are. They will be in this order. And a quick outline of the talk. So first, I will say a few words about the general concept of contact integration, because that's maybe something different than you normally learn during numerical classes, numerical courses. And that's not, I think, even on our faculty, it's not a standard thing to teach. Then I will say the necessary notions about the contact geometry, and then smoothly go to the symplectic formulation proposed by the couple in front of me, and then I will focus on my research. So I will show what mechanical examples, mechanical or less mechanical on Möbius strip examples, and then I will show my results, or what works and what doesn't work. So let's start with the first slide. And the general idea of a geometric integrator is, it is a big word. This is a numerical scheme that aims to reproduce the analytical solution of an equation. We refer to differential equation that has some underlying geometric structure. So, for instance, I will give multiple examples of mostly of solutions, but when we have some differential equation that we consider some, for instance, symmetries, and we'd like in our numerical scheme to encode this symmetry so that it reproduces the actual result as close or as good as possible. This is particularly important when you consider for a long time range of integration, when you would like to, for instance, in celestial mechanics, you would like to obtain a valid solution after longer time of integration. So, for instance, years of or something like this. Then you would then standard methods may work better on a shorter time range scale. So for a short time, you can use the Kutta method, and it works good. But then for a longer time of integration, then because the error will grow, whereas here the error will from the beginning will be a greater error, but it will be bounded and will oscillate during time. So it is the error doesn't explode at certain point, or at least should it. And there are many examples of integrators that we consider depending on the geometric structure that we use to formulate it. the most studied and most well known are symplectic geometers coming from the symplectic geometry. That's the simplest, but also like in mechanical examples, pretty important type of geometry that we have a symplectic structure. And but there are also other. There are variational integrators, multi-symplectic integrators in the topic of field theory. So you can consider many type of them. And there are some approaches how to use a contact structure to obtain a contact integrator, let's say, but it's not clear. There are, I know, few approaches from the literature, but this was kind of a semester project. This didn't, the aim wasn't to actually find the best one or to explore them all, but rather to apply a certain numerical scheme and obtain whether that works. So we will use with Ms. Kasia a different approach. But so why they would be an important contact geometrators topic? Well, in the presence of dissipation of energy. So when an energy is not constant in the system, then you cannot use a symplectic geometry framework, and then you would like to use a contact geometry to encode your dissipation of energy. And
but very particular. This is not general.
Also, you can
dissipation.
Well, yes, but for instance, for a damped harmonic oscillator, it is actually dissipation.
The claim that you cannot use symplectic geometry is not completely true, because you can use forced Hamiltonian systems. So model a system with dissipation and you add the dissipative terms into one external force.
Okay, maybe true, but you can also use in this scheme probably contact geometry would also work.
At least in the literature, some people claim that this is dissipative approach to dissipative.
Let's agree that we can apply it to some dissipative systems, like as an underlying geometric structure.
Okay, so now a few words about the as I will use the symplectic geometry integrator, then few basic words about the geometric and about the symplectic geometry. So this pretty standard clause that we pretty standard topic during lectures to talk about it. So maybe be brief. And as general, we've got some symplectic manifold with closed non-degenerate two-form that we call the symplectic manifold, and on this we consider Hamiltonians and the associated function f. So maybe this is not necessarily Hamiltonians, but for to a function we can define that it's Hamiltonian vector field, which is defined as interior product of xh is defined as a formula 1, let's say. And it can be plus or minus depending on the convention.
I think it is clear from this formula that in this situation you should try minus dh. We check the vector.
Fortunately, the vector field is as it should be. So
yeah, vector field it should be. So
as it should be. So
this is either
minus
contraction from the right or minus dh. This is in order to have a map from function to vector fields being homomorphism of brackets. Yeah. Okay, but
this is, I mean, just a sign error.
this is
so
minor technical remark.
So sorry.
One has to be careful writing the definition of Hamiltonian vector field, because of course this also depends what form you use.
Mm-hmm.
Some people use dqi.
dqi, yes.
Well,
No, but of course, if this is minus
I propose that we do not really linger on the problem of the error
Yes,
with
minus.
minus. Yeah, so this is the problem with minus. And
Okay, yeah, so sorry.
But the definition depends on what form you use.
And we define a flow of Hamiltonian vector field to so it's pullback preserve the symplectic form. Then we call such map from symplectic manifold to symplectic manifold symplectomorphism. And the idea of symplectic integrator will be to produce such a numerical scheme so it reproduces the actual symplectomorphism as a map as close as possible. So I think that's a nice picture. So because in numerics we don't have smooth function, we have some steps, and each step will differ from the analytical solution. At least it should. We have some accuracy that we can reproduce on the computer, but it should follow the analytical solution. That we would call such a numerical scheme, a numerical flow of a general map, and when it's applied to a symplectomorphism, then it would be a symplectic integrator. And a general, so we can define. Usually you would consider one time step at the moment, and the sufficient condition for this map, big psi, and at one time step is that it's a symplectic integrator when it's symplectomorphism written at the bottom. So that would be, and this is psi of delta t is just a one-time step integration.
Yeah, this is phi. Phi of delta
sorry.
t, this is one step.
Yes.
And this is supposed to be a symplectomorphism.
Yes. And a few examples. So we start with examples that aren't symplectic integrators. The two well-known integration schemes are explicit and implicit Euler schemes. So the formulas are a bit lengthy, but they are written, they're displayed in Blackboard. And yeah, so the important thing will be actual the changes in the symplectic form. So we see that in both cases, the symplectic form is changed after just one step of integration, and it either grows or gets smaller. So this is pretty evident in this example. In this,
What you wrote is for special Hamiltonian, I think, yeah?
sorry. Yes, this is for a harmonic oscillator.
I mean, this is general, and this is for harmonic oscillator. Yes.
Yes. Yes. My fault. Sorry. Yes. So the general term combining with the derivative of Hamiltonian is of course a general scheme, but the equations on the right are for harmonic oscillator, and for in one dimension harmonic oscillator, the symplectic form will be just volume form, so we can easily see how it changes in the example. So we see that for the explicit Euler scheme, the symplectic form grows, and for the implicit one, it gets smaller. So that would cause in the first example, the energy of the system would grow, and probably in the second one, it would decrease. So that's not what we would expect from harmonic oscillator solution. Okay, and that's example I did during some simulation course. So this is a Kepler problem in general, and the initial point of the particle is this red dot, and we see that the orbits are not elliptic, which is a sign of bad behavior. And this is done by, I believe, explicit Euler scheme. And two symplectic integrators now. So there's a symplectic Euler scheme, and it contains mixed the derivative term of the Hamiltonian. There's mixed Qn and pi n in the in the next step. So you can prove by some calculations that it is actually symplectomorphism will be. And the more you commonly use centered Euler scheme, or I know it's by leapfrog scheme. So it calculates also the midpoint energy positions and velocities here during your numerical integration, and this is a symplectic symplectomorphism. So also the evolution of harmonic oscillator volume form or symplectic form for harmonic oscillator. The shape may be changed, but the volume form should stay. And in this scheme, at least for a reasonable time of integration, it is the case. So what's evident from this picture, and also that when you solve a Kepler problem with the leapfrog algorithm, you obtain such curves. So it is elliptic, and you see a greater stability. So this is consistent with more or less analytical solution. So we see that there is indeed a difference between applying just any numerical algorithm to the problem and looking at its geometric structure and choosing the appropriate one. So we can imagine that if you want to prepare a mission for NASA and we show them the first Kepler trajectory and the second, they would probably choose a team who shows them the second picture. Yes, and all right. So now we go to the world of contact geometry, which is a bit more challenging, but yeah. So how we defined it, I assume that maybe not everyone is familiar with this notion. So we have some manifold M, and a regular we encode it with or consider
So do you have some natural measure of goodness of the solution and its departure from the analytic one? I don't know, using the volume, symplectic volume form or what? Somehow you should be able to say that this is, because these are just drawings, right? And
yes, so
if you zoom in on one of them, it will spread, right? So what is the measure of goodness?
So normally it depends on the problem you consider. So when it's a non-analytical solution, you can compare it. But when it's not, for instance, you can check how the energy. You can plot your energy and look how it behaves under your numerical
No,
scheme.
in the symplectic case, in the Hamiltonian case, you know that the energy should be conserved. Yes. So
when you've got
even
big,
if you don't know the solution, you know that you have a formula for the energy, so you can check how bad it is.
yeah,
How much it is not conserved.
From the energy.
Now,
Yeah.
for example,
so if you see like exploding of energy at some moment, that's a sign of bad algorithm, because then you go from the symplectic regime.
and also this volume, you can measure the change in volume.
So
But something is wrong with your definition. Do you assume that C is current one in odd dimension or not? A priori, of course, C could be of arbitrary current. But
No, but this is not I mean.
I think this is included in the definition of contact demand.
Slide. I mean, now this is a preparation.
But
Yeah.
the point is that if you see, if C is odd dimension, because this is a skew symmetric form.
Yeah.
So it cannot be never non-degenerate.
What is not the? I mean, I think it is correct. I mean, you have here a form with values on C with values in the quotients. Yes.
But skew symmetric two form on odd dimensional vector space cannot be non-degenerate.
Okay, but I mean, it is If
there
it
are
is non-degenerate, so if it is not, it is not. I mean, this is not the problem. I mean, it doesn't
Yeah, so
satisfy the
they-
definition. This is the
The point is that in some ranks, there are no maximally non-integral.
Okay,
So
okay,
the
and what's the
definition
problem?
doesn't make sense in some dimension.
Okay, I mean, that's true. However, then we
It's
can
saying,
proceed.
but if
probably
you can
we can
refer
add that the
it,
CS
just saying that it is of maximal rank.
Okay. Maximal rank.
Maximal rank, yeah, then of course you don't care whether this is not the general.
All right. So,
But of course,
so let's assume that C is
This
even
is
dimensional.
irrelated to your principal subject, but just to.
Okay, so maybe stick to C. We'll consider
Contact,
even.
of course, deals with core one in odd dimensions, so this
Yes.
is even dimension.
So C is even dimensional and M is of odd dimension. And let it C be a regular distribution. So then we can define this quotient by this distribution and consider a two-form defined on this. So one can check explicitly that this is a two-form, so it doesn't depend on the values close to in the neighborhood, but it only depends on the value at the point. And we would call this distribution maximally non-integrable if it's non-degenerate. So yeah, and the contact manifold we'd call a manifold M equipped with such distribution of codimension 1. So it's written here.
Yeah, so from this distribution, it follows that the dimension has to be odd.
Yes.
Yeah, the dimension of the manifold has to be odd and the distribution even.
But you can consider also weaker concept that contact, this.
Yeah, okay, but
assuming
this is just a preparation.
Assuming what is the rank of this?
Yes, and so working with distribution is usually, at least for students, not that convenient.
So from your definition, it follows that the manifold must be odd dimension.
Yes, precisely, and the C is even. And like, at least for students, working with distribution is sometimes less convenient. So one can also define this distribution, at least locally, to be a kernel of contact form. Yes, here. Okay, this contact form is not unique, can be multiplied by non-vanishing function on its domain, and this will still give a good distribution as a kernel. And the condition of this maximal non-integrability can be a phrase in the language of contacts form. So taking eta wedge product with the eta n times, assuming that the manifold is of dimension 2 n plus 1, and that would require to be non-zero. So one can see immediately from this definition that not on every manifold one can introduce a contact structure.
A contact form.
Yeah.
Form.
Contact
Global.
Contact form, because this form will be of rank 2n plus 1. So this would be a volume. If it were global, this would be a volume form, which won't work on non-orientable manifolds. But we won't find a global volume form. Okay, and few examples. The simplest one would be in R3 with three coordinates, and this contact distribution would be spanned over the dq plus p dz and the dp. So this is indeed even, and the say canonical contact form would be dz minus the Liouville form. So that would be distinguished, but of course we can multiply it by some non-vanishing f. And in this case, this is the simplest one I think we can consider. It is a global contact form. So the second example is is isomorphic to first jet of manifold Q.
First set of functions.
Yes, first jet of functions of manifold Q, and let's denote it in coordinates as Qi, I, J, and Z. And again, distribution is very similar. You just have to add indices in it.
Let us note that the distribution spanned by vector standard to the jet prolongation generally is called Cartan distribution, yeah, or in jet bundle. So this is a particular example of the Cartan distribution.
What is L star?
Sorry?
L star.
It is the next, I mean, it wasn't, I mean.
Oh, sorry. So let's
This is of course irrelevant. This is dual to element, of course. You can explain.
So why L star, not just L?
Because then in application, it is
You start with
more
L
convenient.
In your application, but in our application is vice versa.
It doesn't matter.
Okay.
When the first jet of any line bundle is a contact.
First jet of
However, it will be easier.
Yes. So there was already discussion about the third
So
example.
these Cartan distributions are very important in theory of partial differential equations, understood as certain submanifolds in jet bundles, but this is just digression.
Thank you. So we consider this third example, a line bundle. The line bundle is a one-dimensional vector bundle in general, and we can consider its first jet of the dual bundle. So a dual would be this vector space of this like.
So we know
You can
what's-
just
Yeah.
start with a line bundle.
Yeah.
Yeah,
I mean,
it's
this
also a
star is
contact
not-
manifold. And similarly, the contact distribution would be spanned by jet prolongations of sections.
Yeah, this is the card.
Yes, and so locally it is isomorphic to the second example, but global maybe some differences logically. And yes, so let's go to the topic of dynamics. And like in the literature, usually it's defined by the Reb vector field and then contact Hamiltonian vector field. So a Reb vector field is defined by these two conditions. So it's inner product with eta is 1 and with inner product with d eta is 0. So it depends on the choice of the contact form. In general, it can be only defined locally.
But it is uniquely defined by this condition.
Yes. It's defined, but when we choose different contact form, that will get a different field. If we multiply by a function f this contact form, then we would get a different vector field, not only in the magnitude, but also in direction. So that's, as I understand, pretty problematic. But anyway, it can be used to define a contact Hamiltonian vector field. So we usually associate with functions on the contact manifold, and they are uniquely defined by these two conditions. So when you take inner product with eta, you get minus h, and with inner product with d eta is the h minus rep on h eta. Yes, and that's it defines it uniquely. So I mentioned that. So maybe last 2 words about this contact vector field, Hamiltonian vector field. So they are less convenient than symplectic, let's say, vector fields, or in general in symplectic frameworks, because they are not symmetries of a contact form, but rather symmetries of a distribution, of the contact distribution. So when we take a Lie derivative with respect to this contact Hamiltonian vector field. This will be of a section of the distribution. This will still be in the distribution, in the contact distribution. So this is important because in Hamiltonian framework, symplectic form is preserved by contact by Hamiltonian vector field. That makes easier the constructing the numerical integration. In this context, it is worse for you cannot apply the same strategy, and you have to use a different path if you would like to formulate a contact integrator. And let's now go to this symplectic formulation, which will allow us to introduce a symplectic integrator and is a core idea of the product, let's say. All right, so we define a symplectic principal bundle to be just R cross the principal bundle of a homogeneous symplectic form. And so the homogeneity condition is phrased here. Is here. So when we pull back by the action of this R cross the group, then we get as omega, and that would be a definition. And what we define them, as it turns out that you can uniquely, like up to isomorphism, construct a symplectic principal bundle for a contact manifold, and similarly for every contact manifold there exists a symplectic principal bundle. So M, you can always construct for given M, you can always construct P, and for given P, you can always construct M.
So this is an observation which can be applied to many situations where you want to do something with contact geometry, as you just regard contact manifolds as particular symplectic ones.
Yes. Well,
not only to integrators, but in many other situations.
Definitely. But in terms of this integration, it's nice because you know how to integrate on a symplectic manifold, and as I will show in a second, you can then project your solutions on the contact manifold. So that was the main idea. And so maybe sketch of a proof. The proof is pretty arduous. So consider we take an annihilator of a distribution and remove a zero section.
So sorry, you probably should, say what we are doing. So we are showing first how to pass from contact manifold to the symplectic, how to construct the symplectic counterpart, and then you go with the other way around. Start with the symplectic homogeneous bundle, and then you show how to construct a contact distribution.
But your C is not a contact manifold, it is a contact distribution.
Yes, sorry.
C is a contact distribution on a manifold M.
Yes. But then we can take an annihilator and then remove a zero section, which will be a submanifold in cotangent bundle of M. And when we remove a zero section, we can easily introduce this star action. This will be just multiply covectors by numbers, and then we define P to be this annihilator with zero section removed. And when we restrict the canonical,
so you show that this is a symplectic submanifold. This is important part of the proof.
Yes.
And C always, of course, a line bundle, because this is annihilator of Courant gradients.
Definitely. And so yes, and one can show when you trivialize by a contact form, then it is indeed omega. Omega will be a homogeneous symplectic form. Right, then go to the other way. So we now would like to construct from a given symplectic principal bundle a contact manifold. and we choose by choosing some section, we can introduce locally a vertical coordinate S, and
I'm sorry, but for multiplicative structure in a cross, generator is not S, but SDS. This is DS is in the additive picture, yeah?
Yeah, true, that's true, that's. Mhm. Sorry,
Because
that's why.
SDS generates multiplication by reading.
So S is missing here, true.
I got distracted.
So you can make the change of coordinates R equal
No,
to
okay, but
the
it is written
S
the, yeah, but it is written the S and it should be SDS.
Anyway, if we probably improve it, then by pulling back, we can show that pullback of omega is given by S omega. And from this, we can calculate a lead derivative of omega, which would be just a derivative with respect to S. So it is omega. And by the Cartan magic formula, we can find that omega has a primitive form, which will be ds omega.
So if we just consider this ds not as usual vector field tangent associated to the coordinate, but just as a symbol that denotes the generator of the air action, then it is correct.
Yeah, you see, ds depends on the choice of coordinates. Why SDS comes from the action multiplication in the fiber, and it is independent on coordinate. In each coordinate xs, it is of the same form as ds.
Yes.
And this is invariant vector field.
No,
then
but it is clear.
important.
You see, you get that omega is d, and you contract omega with ds. Then not.
Okay, so maybe.
Yeah, so you have no ds at all. Yeah. So. Okay.
Okay.
So
But
you should think it over. Yeah. What is there?
Okay.
Of course, you can use a symbol for this generator and produce the slide as it is.
So let's assume this. And then one can show that theta, given by the contraction of ds with omega, is homogeneous. So if we divide it by the local vertical coordinate, this would be an invariant. And an invariant on this principal symplectic bundle will be a pullback from a contact manifold. So it will be pullback of some form. And by explicit calculations, one can see that it is indeed a local contact form. And we can define a contact distribution to be its kernel. And by explicit calculations,
well, I guess it has to be actually basic, which it is. Not just invariants, right? But also horizontal, which it is.
It is.
Yeah.
It comes from the
But
contraction. But just mention that if I were to draw a general conclusion, it has to be more than invariants to be a pullback, right?
Okay. Yeah.
It has to be basic.
Yes, and we can see that if we choose a different.
The kernel is invariant. Kernel.
No, it's basic because it is itself a contraction with the fundamental vector field, and it's automatic.
This form theta, which is called the Wheel form, is homogeneous of the V1, but the kernel is invariant distribution, so you can do that.
Okay, so maybe the last remark that it can be proved that if we choose a different local coordinate, then it will produce the same distribution. So it is well defined. It doesn't depend on our choice of section. And yes, so now the words how we will actually So what we will do to obtain why it is introduced, maybe let's if we consider homogeneous functions so then the dh on the symplectic manifold, if we consider homogeneous functions with respect to, if we go to the different point in a in the vertical, let's say, direction, then this should be multiplied by a respective number, and then if we choose functions that will be homogeneous in this sense, then dh will be a homogeneous one form, and in such case this can be shown that xh will be an invariant vector field, so doesn't depend on the local coordinate, thus can be projected on the base manifold, which is contact. So that's written, summarized in this theorem, that if we take homogeneous function and associate a Hamiltonian vector field, then it will be projectable, and it will project exactly on the Hamiltonian contact Hamiltonian vector field. So we can do this in different directions. So on the contact manifold, we upgrade it to the symplectic manifold. If we do it appropriately, then we will land in this. For the respective contact Hamiltonian vector field will land in this projectable one, and we can use the symplectic integration method and then project it on our base manifold.
So you see this dissipativity appears exactly in the process of projection of the vector field. XH is a God-given Hamiltonian vector field, and this is not dissipative. You project a vector field, and of course its properties will change. So this is how dissipativity appears. Yeah.
Yes, and it's like balanced by growing up in this symplectic, let's say, this vertical coordinate. So then it will grow up. Maybe go back. So as I mentioned before, if we consider the first jet of the dual bundle, then it will be canonic. It will be a contact manifold, and this will be an example that we'll use in the. How are you received the question?
Excuse me, but there is one important remark you have not given, namely this H. This was a homogeneous function on this principal bundle.
Yes.
If the bundle is trivial, you can obtain homogeneous function upstairs just multiplying functions on the base by S. But if the bundle is non-trivial, you cannot obtain homogeneous functions out of a function on the base. Therefore, your Hamiltonian is not a function on the contact manifold, but a homogeneous function on this symplectization, or homogeneous functions are the same as sections of a certain line bundle. So your Hamiltonians are sections of a certain line bundle, not a function on the contact manifold. This is fundamental difference between Hamiltonian and contact mechanics.
However, in case of integrators, you do it in coordinates,
Yeah.
so you do it locally, so you can just choose a section and associate a homogeneous Hamiltonian with a function, evaluating it on a section. Yeah.
No, but then,
And this is what you do.
but then, of course, your Hamiltonian vector field will depend on the contact form you will choose.
The Hamiltonian depends on the contact.
Or Hamiltonian.
Hamiltonian, But because it all depends on the
Yeah, yeah,
section. Yeah.
So this means there is no Hamiltonian as a
Yeah.
function.
Geometrically, yes, but practically, it's another matter.
All right, so lots of formats. And yeah, so let's go back. As I mentioned before, there's contact structure on the first jet of a dual bundle, and the respective principle of symplectic bundle is given by a cotangent bundle of L with a zero section.
And you see, Pago,
This is why
the stars
start.
needed.
You start with L, you pass to cotangent bundle, and you L.
Yes, so that's a bit tricky to show actually, and one have to use some. Well, has to understand the structure, yeah. But in the case of a trivial case, so when we've got some manifold times R, then the picture is simpler, and we've got M is just a cotangent bundle times star times R, and yes. So one last thing maybe before going to some actual integration, numerical integration, how we do it in coordinates, because this will be pretty important, and let me say a few words about this. So if we choose Qi and T to be coordinates in a line bundle for T non-zero, and Z to be dual to T, then of course we can have coordinates on the first jet of the dual bundle, and yeah, it's basically written. So this
is the tricky part.
Yes, this is the tricky part, the projection. So for P, yes, so we've got this from the from P we've got an action of S defined by the formula, or not formula, defined on the top, and then the important maybe thing, as we're slightly running out of time, is this projection from P to M. So you have to this P on the contact structure on the contact manifold. It gets is projected in invariant when P is pi I divided, oh, it should be pi j divided by T. And this was
it's here.
Yes. And details can be found in article 1. So I think that's yours. Okay, so going through this theoretical, now should be easier. And two mechanical examples that I consider in practice were a damped harmonic oscillator, and written in their book coordinate Hamiltonian is given just by normal harmonic oscillator minus the lambda z. And for simplicity, I put P and K equal to 1, not to bother about some changes of values too. It was meant to be from a geometric point of view. So, and to obtain a dissipative system, you need to put lambda to be negative, and this homogeneity condition of a Hamiltonian, the principal bundle, which is in this case there's the cotangent to Q times R time. It's given here. The condition to be homogeneous, and then the homogeneous Hamiltonian on the principal symplectic bundle is given by formula 10. So, so one can show if you apply normal, you write Hamiltonian equations, then will be non-separable, and you have some mixing of coordinates, and you can separate it just to be Q, P, and TZ.
Yeah, so we didn't discuss what it means to be separable in this context. So in context of symplectic integrators, separable means that the Hamiltonian is kinetic energy plus potential energy, and kinetic energy depends only on momenta, and potential energy depends only on position, and then it is easier to construct an integrator. And here it is different. We have momenta and position, which is, from this point of view, it is T is a part of a position. So
yes, so
this
it
depends
makes
on the
sense.
position, and also this depends on also on the position. So kinetic energy, in a sense, depends on the position. So this is from the point of view of constructing integrator, it's wrong.
No, but this T doesn't live on the contact manifold,
okay.
it lives in
Yeah,
fibers.
okay, it doesn't matter, but what you do, you integrate up there. So you deal with the symplectic thing and you integrate. So T is important.
So clearly you work with the trivial bundle. You fix the, because you
Well,
just
that's a trivial case.
add the
Yeah, this is the simplest example. You have a triple bundle.
T is add by hand.
Yeah.
Yes, but yeah, but on the symplectic bundle, this would be as your like normal position coordinate.
Because
Consider.
how you choose T depends how the Hamiltonian will look like.
Yeah.
I think what he meant can be rephrased that if you consider that the coordinates for the symplectic form, then the P would be one of the Q's.
Yeah,
So you have a term that combines Q's and P's.
Yes.
Yeah.
And the second example would be a Möbius strip, but more precisely on the first jet. So that's standard the picture for Möbius strip. But you think more of a first jet of this Möbius strip.
So first of all, the vertical direction
should be as infinite. Yes.
Not an interval, but the whole arc.
Yes. And then it was to make a picture of what we were more or less aiming, and the Hamiltonian we choose is given here by formula 11, and as I understand, there is no canonical way how to choose it, but that's the one we considered.
Yeah, so this Hamiltonian is just invented for some purposes, but it lives on this Möbius strip, and it is a geometric object there, even though it is written in coordinates here.
Yes. And if we play the same game and we obtain a homogeneous Hamiltonian, so again we will have some mixing of momenta and position. Let's go. So this will be again a non-separable system. And there are known schemes about they are known for non-separable. I will tell in a moment. But in general, in the literature, mostly studied are the separable Hamiltonians, how to construct an integrator for them. But in this case, the Hamiltonian is not. And I'd like to thank Piotrek for giving an article where this is actually considered how to deal with such systems. And then the idea is to double the phase space. So we consider it on a doubled phase space. So Q pi is the first copy of coordinate on your phase space, and XY is a second copy, which in general can be vectors, can be a bigger dimension. But to make it more or less compact, I keep it like this. And consider a Hamiltonian, which first of all involves mixing of the original Hamiltonian. So we've got the coordinates in the phase space are mixed properly in the equation 13, and there is this omega term with omega. So HC is sort of an official term to keep the solutions closed, and omega is so it measures their binding. So for bigger omega, there should be bigger binding. They should be closer. And the idea is that the general Hamiltonian system given by equation 14 is equivalent to considering Hamiltonian system on this doubled phase space with appropriate initial conditions. So the equation 13 and 15 give the same solutions. What I mean that if we so that they reproduce the original solutions Q and pi if Q and pi were Hamiltonian coordinates given by 14 equation. And yes, so That's a numerical scheme that was applied in both examples. And we construct an integrator by defining three. I wouldn't like to call it flows, because flow would be for an actual integration, but three transformations, which are written here. So phi I, phi B, and phi C. And maybe I would like to know that phi C doesn't depend on the Hamiltonian, so it's pretty universal structure, and full integrator can be built out of these three transformations by the formula 19, and then you get a symplectic integrator by this in more or worse, or in better or worse sense. And the last part of my talk will be devoted to the results, because they are, in some sense, nice, but there are some problems. So first, the results for the damped harmonic oscillator, and the first thing that I checked is how the phase-space plot looks for this, and you can see that there are two plots on the same picture, and they are projected on one another, so they reproduce correctly. So if I go back slightly, this is actual. This is this condition that they project on the same solution, this phase space that they match. So I read here it with with tilde coordinate, and these were copies of the initial coordinates on the for the harmonic oscillator. So they are projected on the same phase trajectory, which is first of all a sign of that the numerical scheme works. And yes, that's
but damped harmonic oscillator you can just integrate by hand. So as I understood that this is the comparison with the actual solution, and this is not. This is the comparison of those two
So
projections.
I will tell when it's comparison with a numerical, with analytical, with an analytical solution. But this is this was to check whether they actually project on the same solution, this would break the idea, because when you double your coordinates, you would like to make them, you want them to reproduce the same solution. And here's some exemplary plot of a position in time, and we see here, yes, we've got an analytical solution in red, and a numerical solution with dashed blue. And so we see that they again project, that they are the same, basically. At least on this picture, you cannot, I think, tell the difference any. And it was done for a pretty long time. So T, then at the end, the solution converges to zero. So there would be less changes in the energy. There is how the energy changes during the integration. And first of all, we may see that the energy difference oscillates during time, which is characteristic for the symplectic integrators, as I mentioned. The energy difference is from the beginning, has some value, but in principle, it shouldn't grow. This should oscillate, but should be bounded. And the reason why it goes to zero is because the solution converges to zero. So there is less space to be any difference, let's say. And by numbers, you can see that, here there's the energy, how the energy changes during time. And it starts with some 1.2. This would probably be joules or something like this. And here is e to -5. So it's at least the energy, accuracy is 3 magnitudes smaller than the actual energy analytical one. So
what you call energy, this Hamiltonian downstairs?
Yes, downstairs.
Yes.
Which doesn't exist.
Okay.
Because but the energy diverges to zero. So there is that would call in energy. That wouldn't make, then energy should be conserved in the symplectic Okay, so yeah, and that these are the results for the harmonic oscillator. I did it for lambda 0.1, a pretty small initial momentum. So when I try to integrate it with greater lambda, it blow up. So I assume that this may be a reason, this may be cause for, because computer for bigger lambda and such small initial momentum may fail from this.
So the problem is that you divide by t at some point, which analytically is different from 0, but when you compute it, you might get close to 0.
Here, because the division in the numerical scheme is not problem here. I think that this should be something different in this case. But the problem what Kasia has mentioned will be evident here when we analyze solutions on the Möbius strip. So here is evolution of this p coordinate on the Möbius strip, and in general it reproduces. So these are both, again, these two solutions, and they are projected more or less on one another. But there are some problems crossing zeros. So then you, I think, indeed divide by very small numbers, and the numerical precision, well, it doesn't work as good. But in the longer term, they are the same solutions. So that's one thing that I may pursue further. So that's one thing to check it more accurately in the longer term. And it also here it may be visible better how the x coordinate behaves. And in this time we don't see any discrepancies. That's because there's no division by t in the x algorithm. I think it only occurs in p. So that's why we have some accuracy here, some differences, and they are even more visible here. So crossing by small and big numbers in this symplectic coordinate, they are, I think it gains some numerical error, because at least on a theoretical framework, this should be the same solutions. Because again, they are projected on, they should be projectable to the same solution from this doubled phase space. And this is again behavior from the x coordinate. So we see that it is smooth and it works better for x's. So,
and here we cannot compare with the analytical solution because we don't have it.
Yes, so that's maybe more problematic to understand. It would be more difficult to catch where's the actual. Is it the method? Is it the computer accuracy? Not sure. That can be a further thing to check. And all right, so thank you for your attentions, and I'm happy to answer questions. Although I think there were many during the presentation.
And according to Trans-Carpathian tradition, we have some parts of Carpathian Mountains.
Yeah.
So thanks for ending with the Möbius striptease. That's very nice. Any questions?
I have one. Going back to your example of the damped oscillator, the Hamiltonian. It's clear what the meaning, physical meaning of x of p. What is the physical meaning of z?
This is this contact chord. Well, physical meaning, this is actually difficult.
Here, lambda z.
Lambda is some constant. But
What is it?
It isn't, I mean, there is no physical meaning. There is
What is it? Rationally, you can interpret it as reaction.
Yeah, you can, but
What coordinate?
it is a ghost coordinate. It is an added dimension. It is an R coordinate. It is an added dimension from my point of view with no physical meaning. From his point of view, there is some physical meaning because they use the Lagrangian picture with the Legendre transformation, which is applied only to those xp coordinates, and then they obtain the Lagrangian picture in which z coordinates has a meaning of Herblot's variational
Okay.
functional.
So that is Kaluza-Klein code.
No. And it is not. Because Kaluza-Klein coordinator is, does not give a contrast.
No, okay, it is.
It is.
It's just Kaluza, big Kaluza.
Oh, this is of course.
Why don't we start with the Lagrangian function?
Because
And
this,
you can define Lagrangian, which is not a function on the tangent boundary. It is rather one. Anyway, the condition is that the Lagrangian and Hamiltonian are functions. It is not correct in the case of dissipative system. You have the Hamiltonian description of the system with viscosity, for example, or fraction. You don't have Lagrangian as a function. Anyway, you have this dynamics generated.
Yeah, and you can
and
generate
you can go perform properly the Rand transformation. You will get something on the Hamiltonian side, and you will see, do we have this contact structure or not?
No, and the answer is we don't. However, when you do it as you propose, so you start not from a function but the same section or one form or whatever, then the dynamics you generate is not symplectic in the sense that it does not conserve a symplectic form. Therefore, this numerical integration procedure cannot be used. I mean, it is not adapted to the structure.
so you see this,
So
this Hamiltonian was
We use a different integrator.
okay, we know that. We probably can.
Function, the contact manifold, but a section of a certain line boundary over this manifold. Therefore, the problem is this section preserved by a diffeomorphism on the base is absolutely wrongly posed. Yeah, so therefore, speaking about
Energy conservation.
how it's
Hamiltonian.
called, dissipativity is nonsense in this case, because what means that a section of the line bundle is invariant with respect to the to a diffeomorphism on the base.
If you put into one all possible consequences of using Hamiltonian vector
And of course, section
and also you don't have Hamiltonian vector field in the case of this dissipative system.
no, you get some vector fields which are called Hamiltonian, but maybe this is wrong.
You have you don't have a vector field and so on. It depends on the system.
Actually, what you get are exactly, if you use all these homogeneous Hamiltonian, you get exactly what is called contact vector field.
I would suggest forget
So why you call contact vector field Hamiltonian? I don't know, but maybe.
forget being mathematician. And you will get
No, but numerical exams are okay, yeah, because you construct the solutions of certain equations.
mathematics is okay, but you will get more and better if you look at physics, not only at mathematics.
And this is your overall metaphysical belief.
For example, the concept of integrator. You can analyze it. What
No,
does
but
it mean?
you see,
This is only
the guys integrate some dynamics numerically, and this is the solution of the problem.
Yeah, I don't think you.
By the way, is it robust enough so that it produces solutions to problems that were not solved before? I mean, not such exotic problems as dynamics on the Möbius, because I understand that this is purely academic. But
Yeah,
are there some new solutions?
so this is integration of certain contact vector fields.
No, I understand what it is mathematically. Has it produced new results that are of
You know, it is, I don't know how to say it in English, so I will for a while say it in Polish. To jest rozpoznanie walką. We don't know.
No, actually, there is some literature. It is widely used in the general relativity field. People use it to solve some.
But do you use?
No, but not the contact, but this concept of doubling.
I mean, the concept
I mean,
of the
symplectic.
integrator itself.
not this contact?
Not
No,
this
not
contact. No, this contact, it was just a pure exercise to check whether we can apply it to some numerical. So we translated contact to symplectic. So can we use it somehow? But it was just the first attempt to do.
Do we have a contact interpretation or?
No, do you have contact with reality? That's
No, never. We never have.
Okay. Okay. So, are there any further comments? You shut up, please. If not, then let's thank Bartosz for a nice introduction into the subject. Next week with
Yes.